Okay, I again notice a little bit of a hissing sound in the recording because of the wind, but uh, this is global warming, and I'm living in Mumbai. It's really hot, but I'm living now for 3 years without ever turning on the air conditioner, so we have to live with this little bit of a noise. I always listen and make sure it's essentially audible, but also the sound should remind you of global warming. Maybe it's getting a little strong. So let's see. Socioeconomic. So the what is for the future? We already know that the shared socioeconomic pathways were combined with the so-called representative concentration pathways that were used in AR5 assessment report 5 released in 2014, where the idea was to use either the integrated assessment models or an iteration between system models and integrated assessment models to come up with the various pathways in terms of renewable energy, population growth, policies, etc., to see where we will end up in terms of the net forcing at the top of the atmosphere. And we had some pathways that were compatible with keeping the warming to below 2 degrees C and some exceeding and so on. So we were looking at radiative forcing by 2100, RCP 8.5 representing essentially the business as usual scenario. Associated with that was a CO2 concentration, which is about 1200 ppm or so, and a warming which is in the range of 4 to 6 or larger degrees centigrade. And you had some pathways that here RCP 3 PD or RCP 2.6, essentially it's RCP 2.6, which would bring us or keep us below 2 degrees C warming with a probability of 67% or so. And there were middle of the road RCP 4.5 and RCP 6, and there are details as to why RCP 4.5 actually is higher in the transient response here than RCP 6 and so on. So shared socioeconomic pathways, on the other hand, focused on socioeconomic challenges for adaptation and socioeconomic challenges for mitigation as the phase space, and the scenarios focused on things like sustainability, taking the green road, middle of the road here, fossil fuel development, taking the highway, rocky road for regional rivalry, inequality, and so on. And many of the RCP 6 were using a combination of these, as we will see here. So future annual emissions of CO2 here, and a subset of key non-CO2 drivers, which are always essential, because if you want to aim for a certain global warming target like below 2 degrees C or below 1.5 degrees C, you cannot just focus on net zero for carbon dioxide, because the non-CO2 greenhouse gases will add warming as well, as seems intuitive, but we have to make sure we track those. So the carbon dioxide gigaton CO2 per year here for the SSP 5 8.5, so you have to really struggle to remember these. This has got low adaptation and high mitigation here in terms of challenges. Well, I hope the recording is okay. The wind is pretty strong, but I'll listen and re-record if necessary, and so on. So SSP 3, 7, so 8.5 is the radiative forcing, 7, 4.5 is here. You can see SSP 2, for example, is middle of the road, and 4.5 is also middle of the road in terms of RCP, whereas SSP 1, 2.6 is sustainable and below 2 degrees C, and SSP 1, 1.9 is sustainable and below 1.5 degrees C, but we are already behind in terms of where the CO2 emissions have to go to reach those, but maybe some game changer will come along, and by 2050 we're going to hit net zero and so on. Okay, so these are the selected contributors to non-CO2 greenhouse gases like methane in million tons methane per year, various scenarios, nitrous oxide, million tons nitrous oxide per year, and one air pollutant and contributor to aerosols, the sulfur dioxide, in million tons of SO2 per year, which is a cooling one, as you remember. So this is a huge range of scenarios that were used, and contribution to global surface temperature increase from different emissions with a dominant role of CO2 emissions was looked at in terms of change in global surface temperature in 2081 to 2100 relative to 1850 to 1900. So we are now focused on the future. So the benign scenarios like SSP1, 1.5, obviously the warming would be very low here. These are from total warming due to CO2, non-CO2 greenhouse gases, and aerosols and land use creating a cooling. This is the next best one. SSP1 2.6 will keep us sustainable and below 2 degrees C with 67% probability. Obviously warming goes up, CO2 contribution goes up, non-CO2 gases go up, and the cooling remains almost the same. You go to the middle of the road, then you begin to increase the warmings and contributions from CO2 and non-CO2, and here because the land use change would be much more extreme, you also begin to have and fuel use like maybe coal burning and so on, releasing sulfur dioxide, for example. And SSP 8.5, of course, if we are headed this way, then it's going to be very difficult for future generations, but nonetheless we have to kind of track it to see the extreme impacts it would have on the extreme heat events, including wet bulb temperatures, extreme rainfall events, droughts, wildfires, human health, and so on and so forth. So hopefully we can avoid these completely. Looking at the annual mean temperature change at 1 degree C warming, the approach is to look at observed change because we have already crossed 1 degree C, and look at how the simulated change at 1 degree C works. And the message is really that as you increase the emissions and increase the warming, regional changes correspondingly get worse. We have talked about the cooling hole here related to the Atlantic meridional overturning circulation, even though there are details whether the change is coming from here or further north there. But you can argue that the models are doing a reasonable job of capturing regional warming trends as well. So warming at 1 degree C affects all the continents, and it generally is generally larger over land than over the oceans in both observations and models, because oceans have higher heat capacity and have been modulating the global warming by taking up more than 93% of the additional energy being trapped by greenhouse gas increases. Across most regions, observed and simulated patterns are consistent. So again, using this as a confidence builder, then you look at the future in terms of annual mean temperature change relative to 1850 to 1900. Simulated change of 1.5 degrees C, you can see that the warmings would go up with some hotspots like the polar amplification, which just keeps getting worse with additional warming. So this is at 2 degrees C, this is at 4 degrees C. Here you can imagine what would happen to the Arctic ice, Greenland glaciers, and a lot of the snow cover in northern hemisphere, and also Sahara here, Middle East getting hot, becoming hot cauldrons, various regions of the southern hemisphere also getting significantly warm. So additional warming is just going to start amplifying at regional levels with all kinds of consequences, some of which are seen in mean precipitation change. Again, remembering that the model agreements in general tend to be lower for precipitation changes. Nonetheless, precipitation is projected to increase over high latitudes, the equatorial Pacific and parts of the monsoon regions, but decrease over parts of subtropics and in limited areas of the tropics. So there are details. Monsoon trends in the past have not always been reproduced well by the models. So how much can you trust their future projections and so on, and whether they are dynamically consistent in terms of the land warming versus ocean warming and so on and so forth. You can see here that the Indian Ocean warms in the observations. Models may not be doing it as well, and whether the Eastern Pacific warms more or less than the West Pacific will have consequences, and you can see that in the future warmings, Indian Ocean may do something to the north-south temperature gradient and the monsoon and so on. So leaving those aside, looking generally for what can be expected, simulated change at 1.5 degrees C global warming, relatively small absolute changes may appear as large percentage changes in regions with dry baseline conditions. So you can see that the Sahara, for example, which has very low rainfall, small changes can appear as big percentage changes, whereas there are other regions here on the equator, which is now in the east dry and cold, but with 1.5 degrees C it is showing as wetter, so one has to be careful about those. And the subtropics here are generally getting drier. The monsoon region has here some pattern that has to be understood, high latitudes, but you can see that these tend to get amplified a lot. So will Sahara get wetter and wetter with warming, and will the Arabian Sea get so much wetter compared to the Bay of Bengal? Arabian Sea is definitely warming rapidly, and in these projections also it warms, so there has to be changes in cyclones and so on as well. But you can see that the Mediterranean here gets drier. The polar circle here, both hemispheres get wetter, but this can also mean that snowfall changes to rainfall, and a lot of the snow cover will disappear. And here already very complicated things are happening in terms of ocean warming, creating some additional snowfall in some regions, but carving off shelf ice and glaciers in other parts. So very complicated. So one has to be careful about what the models include in terms of the details of the Antarctic, that they can say this, and what is included in terms of land ice in the north to explain these things. And there has to be some consistency again. Is the Middle Eastern warming that is so rapid here consistent with the rainfall change that is happening here? In the observations, for example, during this time, there has been a warming here and dust loading, which is affecting the monsoon in a positive way. Aerosol loading here tends to strengthen the monsoon here, for example. Is that the same thing that is continuing with warming of the Middle East in the future? That's not always so clear. So looking again at the annual mean total column soil moisture, which is not just the surface moisture but something that can explain the agricultural and ecological droughts, relatively small absolute changes may appear large when expressed in units of standard deviation in dry regions with little interannual variability in the baseline conditions. Again, Sahara shows up. Amazon is looking like bad news. It's a very wet region in the present climate, but facing lots of perturbations from human activities and deforestation. But again, details like what kind of vegetation model is included and how these simulations are bringing out these changes in soil moisture in the future have to be understood more carefully. So you can see the pattern, simulated change at 1.5 degrees C warming, 2 degrees C warming, and 4 degrees C warming. Sahara again, Sahel and sub-Saharan Africa light up. Mediterranean is got bad news all over. Western US can be again bad news, which is already pretty bad. Parts of China here appear quite bad, whereas India is benefiting in these simulations in terms of soil moisture and rainfall as well. So if this is true, then again the detailed questions are whether rainfall will be increased but will continue to come as very extreme heavy rainfall events with widespread floods and so on, which is what happened in the last several decades, for example. So just the increase in rainfall doesn't always mean a positive thing, especially because the warming that goes with it, even if there is more rainfall, the warming can be so extreme that crops can begin to wilt, and they are beyond the optimal temperature range for more crop yields, for example. And of course the associated humidity increases with these kind of temperature changes can mean that you are crossing the wet bulb temperature, where human ability to lose the body heat with perspiration may be completely removed, so mortality due to heat waves can go up even at much lower temperatures as humidities increase. Okay, so I will leave this here and then come back and look at some more details in terms of the future projections. Okay, I'm trying to keep these to reasonably long time so that your attention span is not overwhelmed by the details. Okay.